All right, let's continue. We multiply the first rational function, top and bottom, by 2x minus 5, such that the two rational functions right now, or the two rational expressions right now, have the same denominator. The denominator is 2x minus 5 squared. We copy the left-hand side. Right-hand side, they have the same denominator. We can keep the denominator, 2x minus 5 to the power of 2, and then solve the top. Solve the top, we have a sub 1 times 2x minus 5 plus a sub 2. Look at the equation here. Left-hand side, we have a rational expression. Right-hand side, we have a rational expression. They have the same denominator. Shouldn't they have the same numerator? Similar technique we have seen that over and over, right? Or in other words, we have two fractions on both sides of the equation. They are equal to each other. If they have the same denominator, then they should have the same numerator. So let's equate the two numerator. We have x minus 4 equals a sub 1 times 2x minus 5 plus a sub 2. Let's distribute. Remember, a sub 1 and a sub 2 are two constants. A sub 1 times 2x, 2a sub 1x. A sub 1 times negative 5 a sub 1 plus a sub 2. We reorganize organize the right-hand side. 2a sub 1x plus negative 5a sub 1 plus a sub 2. Okay, so now we're going to use the same idea that we did earlier. This is an equation. This equation equates a linear polynomial on the left and a linear polynomial on the right-hand side. Then if the two linear polynomials equal to each other, then their corresponding coefficients should be equal to each other. Firstly, anyone can tell me what's the coefficient of x here? It is 1, right? Yeah. So what I mean is the coefficient of x should be equal to the coefficient of x on the right-hand side. Coefficient of x on the left should be the same with the coefficient of x on the right. Yellow. A constant term on the left should be the same with the constant term on the right. So the corresponding part should be equal to each other, right? So now we would have a system. We have 2a sub 1 equals 1. We have negative 5a sub 1 plus a sub 2 equals negative 4. 2a sub 1, pink equals pink, yellow equals yellow. So now we are looking at a system in two variables, a sub 1 and a sub 2. I know they are just unknown. Technically, they are not really variable. The values of them are going to be certain. It's easy to solve for a sub 1 and a sub 2. From equation 1, we can get the value for a sub 1 easily. Divide both sides by 2, we have a sub 1 equals half, right? If we plug in the value for a sub 1 here, negative 5 times a sub 1, a sub 1 is half, plus a sub 2 equals negative 4. Let's solve for a sub 2. Negative 5 times half, negative 5 over 2. Move this number over. We got a positive 5 over 2 minus 4. 4 is 8 over 2. And that gives us negative 3 over 2. So we got the value for a sub 1 and a sub 2. Let me double check. Half and 1 over 2 and then negative 3 over 2. Yeah, that's correct. So we can make a conclusion. Thus, the decomposition, the original function x minus 4 over 2x minus 5 to the power of 2 is going to be, remember we decompose this function as a sub 1 over 2x minus 5 plus a sub 2 over 2x minus 5 to the power of 2. Remember that. Yeah. So now we have the values for a sub 1 and a sub 2. We can put them back. A sub 1 is half here. A sub 2 is a negative 3 over 2. And this is good enough, but if you want to go further, you can write this as 1 over 2 times 2x minus 5. And this as a negative 3 over 2 times 2x minus 5 to the power of 2. Yeah. What's the benefit? I mentioned that this is useful in calculus because in calculus it's going to be pretty difficult to take the derivative or integration for a rational function. However, if you could decompose them for each part in the decomposition, for each part in the expansion, the derivative and the integral would be easier, a lot easier to get. That's the purpose. This is example 1. Let's see example 2. Example 2, we have a rational function. It is 2x over x squared minus 1. We need to decompose this rational function. It is a rational function because both top and bottom are polynomials. Numerator is a linear polynomial, so degree is 1. Denominator is a quadratic, so degree is 2. So the function f of x is proper. What kind of formula we're gonna apply though? If you look at the note, I have the notes posted in Moodle. Okay, we are going to use the second formula here. Hold on, I'm sorry. So we are going to use the first formula here. It's still the same formula that we apply for example 1, but a little bit tricky. What is tricky? The reason we don't use the second formula because the denominator, even the denominator is quadratic, but is factorable. It's not a prime. We could easily factor x squared minus 1 as x plus 1 times x minus 1. That's the reason formula 2 doesn't apply. In formula 2, the denominator does contain a quadratic trinomial, but that quadratic trinomial is prime. So here, this quadratic is not a prime. It is factorable. It could be factored as x plus 1 times x minus 1. So then how do we decompose? So this one is a little bit different from example 1. We have 2 prime linear here. We have 2 prime binomial here. So we're going to apply the formula, the same formula, the first formula twice here. So firstly, we're going to rewrite, we're going to do this part, x plus 1. The power is 1, right? So we're going to have x plus 1 on the bottom and a constant on the top. We are done for that part. And secondly, we're going to do this part. It is also a prime binomial. The exponent is 1. So for that, for the formula for that part, we also only have one part, x minus 1, and the numerator is going to be a constant. You can see all the decomposition, the numerator always has degree 1 less than the degree of the bottom in all the decomposition, in all the expansion. Is this understandable? So this term is for the prime binomial x plus 1, and this term is for the prime binomial x minus 1. They are both linear, so the numerator are going to be constant. Constant is a polynomial with degree 0, right? Okay, so let's see how do we find the values for a1 and a sub 1, a sub 2. 2x over x plus 1 times x minus 1. On the right hand side, we're going to add them up. We know they are not. We know they do not have the same denominators. We need to find their least common denominator. Their least common denominator is going to be the multiplication of the x plus 1 and x minus 1. So in order for this one has the least common denominator, we are going to multiply both top and bottom by x minus 1. For the second, we multiply both top and bottom by x plus 1. Now they have the same denominator, x plus 1 times x minus 1. We solve the top, a sub 1 times x minus 1 plus a sub 2 times x plus 1. Okay, same thing. They have the same denominator. They should have the same numerator. Okay, so we equate their numerator. 2x equals a sub 1 x minus 1 plus a sub 2 x plus 1. And then reorganize everything. On the left, we actually have 2x plus 0. The constant is 0. On the right-hand side, we distribute a sub 1x minus a sub 1 plus a sub 2x plus a sub 2. Combine like terms. The coefficient of x is the addition of a sub 1 and a sub 2. The constant term is negative a sub 1 plus a sub 2. Okay, on the left, the coefficient of x is 2. On the right, the coefficient of x is a sub 1 plus a sub 2. On the left, the constant is 0. On the right, the constant is negative a sub 1 plus a sub 2. So the pink part equals the pink part. The yellow part equals the yellow part. That's how do we have a system now. A sub 1 plus a sub 2 equals 2. Negative a sub 1 plus a sub 2 equals 0. Equation 1, equation 2, two equations for two unknowns. If we add them up, add the two equations together, a sub 1, negative a sub 1 cancel out, right? So we have 2a sub 2 equals 2, a sub 2 equals 1. And we plug a sub 2 equals 1 back into equation 2. We would have a sub 1 also equals 1. That's how do we solve for the two unknown. Thus, the original function f of x, which is 2x over x squared minus 1, can be decomposed as, we know it was decomposed as a sub 1 over x plus 1 plus a sub 2 over x minus 1, right? So now it is 1 over x plus 1 plus 1 over x minus 1. For the derivative, for taking derivative or integral, those two functions are easy functions compared with the original. You would see, so this actually is easier. It's also easy to take the derivative and the integral. It's just this is just an example. This way is easier. It's just easier. Okay, so one more example. Example 3. We need to decompose function f of x. Numerator is 2x squared plus x plus 8. Denominator is x squared plus 4 squared. Let me double check. 2x squared plus x plus 8 all over x squared plus 4 over 2. All right, so the denominator right now is a quadratic binomial. Even it's a binomial, but it doesn't matter. It is a quadratic, degree 2. Numerator is degree 2, right? Denominator, if you FOIL, you have degree 4. So this is a proper. We check that first. And then we look at the denominator. This quadratic polynomial is a prime. Is a prime in. Now they have the same denominators, right? We solve the top. They should have the same numerator. Equal to the green part. So let's equate the two denominators. 2x squared plus x plus 8 equals a sub 1 x plus b sub 1 x squared plus 4 plus a sub 2x plus b sub 2. That's for you. First times first, plus outside times outside, plus inside times inside, plus last times last. Oops, too much. Yeah, I can move over here. Plus a sub 2x plus b sub 2. Let's fill in the blanks. First, a1x x squared, outside a sub 1x 4, inside b sub 1 x2, last b sub 1 4. Let me double check. A sub 1 x squared, outside, inside, last. Okay, so let's reorganize everything on the right hand side. So this is a sub 1 x cubed plus 4a sub 1 x plus b1 x squared plus 4b1 plus a sub 2x plus b sub 2. Combine like terms. We have a sub 1 x cubed. For square, yeah, we have b sub 1 x squared. For x, we have this one, we have this one. So that is 4a sub 1 plus a sub 2 of x. For the constant term, we have 4b sub 1 plus b sub 2. All right. So right-hand side is a polynomial with degree 3. Left-hand side is a polynomial with degree 2. Then you would know a sub 1 has to be 0, right? Yeah, a sub 1 has to be 0. And on the left, the coefficient of x squared is 2. On the right, the coefficient of x squared is b sub 1. Pink equals pink. From that, we have b sub 1 equals 2. Right? Yeah, we do have 4 unknowns, but we have the values for 2 of them already. Coefficient of x, let me change the color, yellow. Coefficient of x here is 1. We know that is 1, right? And the coefficient of x on the right hand, coefficient of x here is 1. We know that is 1, right? Gives us another equation, 4a sub 1 plus a sub 2 equals 1. Constant, another equation 2. So that gives us another equation, 4b sub 1 plus b sub 2 equals 8. All right. So now we know a sub 1 equals 0, b sub 1 equals 2. If we plug in a sub 1 equals 0 here, we would have a sub 1 equals 1 because this disappears, right? That's 0. A sub 1 is 0. So a sub 2 is 1. B sub 1 is 2. B sub 1 is 2. You plug in here. 4 times 2 is 8. 8 plus a number equals 8. That would make b sub 2 equals 0. Okay, so we have the values for the 4 unknowns. We can make a conclusion. The original rational function, what's the original rational function? Is 2x squared plus x plus 8 all over x squared plus 4 to the power of 2 equals, originally, in the beginning, we decompose the function as this, right? a2x plus b2 all over x squared plus 4 to the power of 2. Now we know the values for the 4 unknowns. We can plug them in. A sub 1, 0. B sub 1 is 2, so we have 2 here. A sub 2, B sub 2 is 0. A sub 2 is 1, so we have x here. X here. Second power. So that's the decomposition of the original rational function. For the decreases, as long as you follow my notes, really understand the 3 examples, I can make sure you get a full points for that decrease. Feel free to make an appointment with me to ask any questions. I hope to see you soon in Zoom. Thank you for watching. I'll see you in next section.